Bonjour.
Hello, Serge.
Hello.
Welcome back, everyone, to the second lecture of today at the Mathematical Summer in Paris. I'm very happy to introduce a regular of the school, Serge Cohen, who has given lectures in all three editions of this summer school. So Serge Cohen works at the laboratory IPANEMA, and you've seen his workplace yesterday during the virtual tour of the Synchrotron Soleil. And so he will speak today about X-ray radiography, random transfer, and the Radon Transform, and the Fourier transform. Please, Serge, the floor is yours.
It's a pleasure to be here for the third time, and indeed, I'm going to talk again of something I spoke on the very first time in 2018, I think, which is mathematics for reconstructing volume from X-ray radiograph. Okay, so this will be the talk. I'll start by just pausing and exploring the term of the problem we're trying to solve today, and then I'll go into the process of image formation, which is what are we measuring, and then a few ideas about transform, in particular the Fourier transform, and finally how from the data that we collect we manage to reconstruct a volume. Okay, so as a teaser. As a teaser, I will just show you more or less the idea of tomography. The idea of tomography is if we have an object as the one you see now on the left, and we measure some radiographs on it, which are represented at the very top of the image. So we measure radiograph while the object is turning. We want to know if we want to be able to reconstruct the volume just from radiographs. Okay, so we will explore what do we mean by radiographs. So what is a transformation which takes the object on the left and makes what is a radiograph, which are represented here on the very top of the screen, and how from this series of radiograph we manage to get an estimation of the object itself, which was displayed at the right of the screen. Okay, so. And just for the video, I will go out and on because the PDF doesn't work for the video. I didn't manage to get it working. Okay, so the radiograph was first used at the very end of the 19th century by a physicist called Cohen, and he discovered something that he called X-ray because he had the intuition there were rays, and the reason why he had this intuition is that because obviously they were going straight. Okay, so he had this thing which was emitting something. He would put the hand of his wife. He was not maybe courageous enough to put his own hand inside, and putting a film on the other hand. And the reason why he says there are some rays is that obviously from the emitter to the film, silver-based film, the energy or whatever particle was there was going straight and was attenuated by the matter in a way we'll see just a bit later, and that's why you say, okay, we have some source of X-ray of these rays which are going through matters which are attenuated by matter, but much less attenuated than visible light, and these rays are also triggering reaction on an argentic film, on a silver-based film. Okay, so that was interesting because it somehow could go inside the matter. So we would see this ray would give evidence of things which are not visible directly by the bare eyes, because bare eyes are sensitive to visible light. Okay, so now we know a lot more about X-rays, and X-rays are just photons as visible light, as UV, as infrared, as gigahertz photons which are used by cell phones or Wi-Fi and so on. So all these are basically photons. The thing which is important to understand is that these photons have some peculiarities. And in general, light and I'm coming back to first object. In general, photons are interacting the matter with a certain the main reaction is attenuation. Okay, so the matter will stop a fraction of the photon, and this can intuitively be understood that if we put a filter, so something which is attenuating photon, it will have a few properties, and the main property is that this is somehow a multiplicative effect. Okay, so we can do a thought experiment, and we have a filter, and here that's what I'm representing here with this rectangle, which is somehow a filter which has different attenuation parts, some parts which are less attenuating, and some parts which are more attenuating. And basically, what the first thing what we can think is that if we double the light, the quantity of light which is coming on what we call the incident light, what we expect is to have double the light on the other side. Okay, so that somehow the kind of multiplicative effect we expect from a filter. And as another way to see it, so the first one is just we double the light, but if we put exactly twice the same filter, a second filter exactly identical to the first one, just beneath the first filter, wherever the filter is producing a division by 2 of the light, as a consequence, we will have a division by 4. Okay, so we don't add, but we multiply the effect of attenuation by a filter. And when I mean filter, is basically some matter which attenuates partially the light. Okay, so obviously if we cut out completely the light, it's very difficult to be able to say that we have more or less light afterward. Okay, so if we go into a bit more detail on that, I have an intensity on the incident beam, which I will call I0, where in the full talk, and I have an intensity which I measure after the filter, and in this case I will say I1. Okay, so I can characterize the filter at a given position by what we call the transmission coefficient, which is T, which is below 1. The attenuation effect is an attenuation effect. It doesn't brings more light. Okay, so there are some effects which are bringing more light, but in the current state, the X-ray, mostly the most important regime in X-ray in this kind of imaging is to get this kind of effect, which is dominated by the attenuation. Okay, if I double the filter, I will square the effect. Okay, so if I put a second filter behind the first one, it will have the same attenuation, which means that at the end I will have the square of the effect, and it means that I can write that in log scale in an easy way. If I take a log scale after n filters, I will get log n log of the transmission plus the log of I0. Okay. So if I take the absorbance, another way of doing that is to take the absorbance and say what I'm looking at is a log of I0 over I1, and this is minus log of T. Okay. The reason why it's yes. Okay. This is for material, and if I go for this is I'm looking at the filter as such as a complete material. But if I try to thin the filter and consider that the object I'm traversing is made of an infinite number of small filters or smaller filters, what I can do is replace this total attenuation or transmit, or more precisely, I can replace this absorbance by a linear absorbance. So basically, taking this view of a single filter as something where it depends on the thickness. Okay, and this is for homogeneous material. And then basically, clearly, if I double the thickness of the filter, which is basically having a second filter of the same attenuation, I will have double the absorbance, and that's why I have this linear coefficient multiplied by the thickness of the sample. Okay, so this is a constant. Sorry, I still have accents. This is for the total thickness of a filter, and it's considering a filter which is uniform in composition. Obviously, this attenuation depends on the, well, I say obviously because we see that a given filter will not transmit in the same way the red, the blue, or the yellow if in the visible light, and indeed it's the same. There are some material which are completely transparent for certain wavelengths and totally thick to other ones. For example, water is transparent in the visible light, more or less. A glass of water, you can nearly see through it. But for example, it's rather opaque to gigahertz wavelengths or photon of gigahertz energy. And that's why a microwave oven, which is in the gigahertz range, is heating water because the water is absorbing this energy of light, the light of this energy. Okay, so this attenuation coefficient depends on the wavelengths. And in the X-ray, and that's the reason why the X-ray are rather interesting in terms of seeing the internals of objects. The effect is mostly a direct interaction of the photon with the electrons as such, nearly as if the electrons were free of all atoms. Okay, so what the X-ray see is a cloud of electrons. It doesn't see the nucleus of or the nucleons of the atoms. And it sees a gas of electrons somehow, and we are going to be sensitive to the density of electron. Okay, so oops, sorry. One thing which is interesting is that if you look at the periodic table, you will see that most atoms have 2 nucleons per electrons. Okay, so the number of nucleons, protons, and neutrons is twice the number of electrons, more or less. And the mass of the atom is more or less the number of nucleus, and the density in electron is then strongly correlated to the mass. So through the electron density, we get some kind of information on the mass density of the material, and we can see that within the depth of an object. Okay. The second aspect is that X-rays, they travel in straight lines mostly. That's what I was telling you, and that's why also Röntgen say they were rays, because from his experiments, it was he had the intuition they would go mostly through straight lines. Okay, and then because of that, we have this relation that if the material is uniform, we can say that the absorbance is an attenuation coefficient which depends on the material times the thickness of the material. But if the material is non-uniform, we can write the same thing as an integral, and then we have a position-dependent density, and the absorbance is going to be the integral, the sum of the small elements of absorbance of all the small part of the object that we are traversing. Okay, so if initially I was speaking of filters, but if we say that we are traversing a material, we can basically consider this material is made of very thin slice, one after the other, and in each slice, which has a thickness of the small element of length dx, in each of these, I will have an absorbance of μx dx. And what I saw before is that in absorbance, because I'm on log scale, I can just sum the absorbance of each element of matter that I'm traversing. Okay, so basically what I'm going to measure for one X-ray, so for one ray which goes through the material, I will measure the integral of the linear absorbance of all the matters which are traversed, weighted by the length of each of these matters. Okay. Okay, so now how do I do the experiment? I have a source of X-ray. So this is a synchrotron that you had a visit of yesterday. And the synchrotron is producing, amongst other things, X-rays. So we have in the case of tomography, we are going to select X-rays, the synchrotron, for example, Soleil, but there are many other synchrotrons in Brazil, in the States, in Japan, in Russia. There are quite a few synchrotrons on Earth. Most of them are producing X-rays. Some of them are also producing UV or infrared, like Soleil. And some are producing very hard X-rays, but none are producing anything more energetic than X-ray, and that's it. So we have a beam of X-ray, and this is a beam which is a parallel beam. So basically the rays which are emitted are nearly parallel. We have a source which is a small point, so it's a very small source of a few tenths of microns, but it's very far away. So at the point we are seeing, everything is parallel, a bit like the light of the sun on Earth is nearly parallel. That's why the shade casted by the sun is a very clear shade, because the rays are parallel. Okay, so we have the same kind of effect here. So we have the X-ray here coming parallel, an object, a sample, which is positioned on a stage, and this stage has a capability to rotate along an axis which is perpendicular to the direction of the X-ray, and then we have a detector. Okay, so here I've put the basis, which indeed is linked to the sample, not of the. We'll see later on that the way we cast this thing is to say that the basis is attached to the sample rather than to the experiment. But currently in this current position, the X is going to the right and the Y is going to the top of this image. Okay, and what I just told you is that for one given ray, which I put, for example, at oops, sorry, I don't know if I can do that. I might be able to, oops, sorry, I want to draw a line. If I do a line like that, oops, okay, so if I have an X-ray which is going like that, okay, this one is parameterized as a Y equal a given value, Y0, and this ray, I realize that this arrow is not completely horizontal, but the aim was that it was going completely horizontal. When it goes through air, it's nearly not absorbing, because the density of air as any gas is rather small compared to the solid object. And as I'm going within the object, the X-ray is going to be attenuated, and at each point, it's going to be attenuated by a fraction, which is the electron density somehow of the point times the length of this density. Okay. Yes. Okay. So now I'm not. What I was telling to you is that I'm not doing a single radiograph. I'm making many radiographs. Okay. So you have multiple. You have two ways to see that. One way is the synchrotron way, where you make the sample turn around. Okay, the reason why we make the sample turn around on the synchrotron is that you cannot make the synchrotron turn around. Okay, you cannot turn around the synchrotron. The reason why I say that is that another place where we're doing very often tomography is, for example, medical science and life science, and for medicine, it's very often you may have to do a CT scan, and in this case, you're going to rotate not the person, because you cannot rotate a person, especially if he's tied up with a different medical device. So in this case, the person with the sample is immobile, is not moving at all. And what is going to move then, you have to ensure that what is going to move is the detector and the source. Okay, so in the CT, within the big the big tunnel that you're in, around the tunnel, you have a big ring on which you have on one side the source, on the other side the detector, and all this is turning around the patient. In our case, it's the opposite. The sample is turning, and the source and the detector are not moving. Okay, so it's basically what is important is that there is a motion, a relative motion between the sample and the detection system, and it can be a bit different depending on the complete setup. Okay, anyway. For simplicity, because what we are going to measure is something which is tied to the sample, we consider that the sample is not moving and everything else is moving. Okay, and in this case, for example, you have the sample which is represented by this blob at the middle, and you have two relative positions of the detection system which are represented. One with this angle, which is called θ2, and another one with this angle θ1. And every time you have this parallel beam which goes through the sample and which is going to be measured on a detector, showing a profile which is going to depend on the angle, obviously. And for each angle, it's going to depend on the path of the corresponding X-ray within the matter. And what is important is that you consider that the X-rays are going straight. Okay, so you can know for a given pixel here, you know that this pixel corresponds to this ray here, which goes through here and which goes to this part of the sample, not another one, this part of the sample. Okay. Okay, so for simplicity, we consider what is immobile to be the sample, and that the reason why is simply because what we try to characterize is a function which is tied to the sample. Okay. What also is important is that the beam is orthogonal to the rotation angle, and here I depicted just a section of the system where if ever the rotation was not perpendicular, what I would have is that so if my beam was parallel to the plan of the slide of the display, but the rotation axis was not perpendicular to it, what I would have is that some part of the sample would go out of this plane at for certain angles, and some other would come in, and which means that depending on the rotation angle, I will not have the same. I would not view the same part of the sample within this plane. Okay. The thing is that if the rotation angle is perpendicular to the beam, then this part of the sample, the one which is depicted here, stays in this plane, and this is the only part of the sample which will ever be in this plane during all the experiment. And that means that I can treat every single plane as totally independent from the other one. Okay, so I can basically handle each planes independently of the others. Okay, so that's interesting in terms of simplicity to understand the problem. It's also interesting because it means that I can process independently each of the problems. So instead of being forced to reconstruct the full volume at once, I can reconstruct each slice one by one, or even I can distribute each slice on a different computer. The computer don't need to talk to each other during the reconstruction. Okay, so in this case, I set z equal z0, and from now on, I will not even speak 3D anymore, because I consider that in this geometry, the problem is a purely 2D problem. Okay. Okay, so I have a line which represents the X-ray beam relative to the object, and this line may be parameterized by r and theta. Okay, so theta, you have it here, and r is basically the distance between the center of rotation and the beam, the ray I'm considering. Okay, so if I'm considering this ray, I can parameterize it as a ray which corresponds to theta equal theta2 and the distance from here to here. Okay, and for given distance here, I have exactly the same distance here. Okay, and that the reason why this happens is that because the rotation axis is at a constant position corresponding to the detector. Okay, so most often you put them in such a way that the rotation axis is parallel to the detector and the detector is perpendicular to the beam, but indeed you don't even really care, because the relative position of the rotation axis and of the detector are constant. That means that this distance is somehow either, if it's orthogonal, it's equal, but otherwise is isomorphic. It's the same. It's just a reparameterization. The distance between the projection of the center, which is I think this line here, to the line. Okay, so these two parameters, theta and this distance, are sufficient. Here it's called t, but later on I will call it r. These two are sufficient and necessary to represent this ray. Okay. So these are the two parameters, r and theta. Okay. So if I'm now sitting in the sample coordinates, I can express the ray as being the line consisting of x and y with a parameter s, which is basically the axis on this ray, and which is s sinus theta plus r cosinus theta on one coordinate, and on the other one minus s cosinus theta plus r sinus theta. Okay, and then what I say is what I measure is the integral on this line of the the attenuation coefficient. Okay, so I'm just plugging these coordinates into the equation I had before, and I get this result. Okay, so basically I get an integral version for any r and theta. Okay, so now let's consider that the function mu has a few sufficient conditions. First one, it's continuous, so that's a rather physically realistic situation. It has a compact support, which also for a solid object within gas, within the atmosphere, it's something which is rather realistic, and it has finite values. We don't have anything weird within the sample. Then we can demonstrate that the integral that I showed you before can be computed for any value of r and theta. Okay, there are a lot of by the way, there are a lot of value of r which are just too far from the object and which will produce 0, and that's not really interesting. What we're interested in is get all the value for which we have a bit of signal. So this attenuation happens. It's not 0. Okay, an attenuation of 0 means the incident energy is fully found out after the object. Okay, so the function which maps the mu, the attenuation coefficient, to the absorbance is a function which is known in mathematics from the very early of the 20th century, which is called the Radon Transform. Okay, so it's called after a mathematician called Radon, and we will note it R, capital R, in a rounded way, just to make sure that we understand that this is a function which takes a function. It's an operator. It's a function which takes a function and returns a function. Okay, so the Radon transform is a linear operator, and you can demonstrate fairly easily that the transform of a function which brings only 0 is 0, and if you do the sum of two objects, so basically if you have an object which attenuation coefficient is exactly the sum of the two attenuation coefficient of two objects, then we get the sum, and the same for multiplication. Okay, and indeed this is a direct consequence of the fact that A is expressed as an integral. Okay, and this is the linearity of the integral which is transferred to the Radon transform of mu. The thing which is important here is indeed not so much of this result, which you can basically write directly. It's the thing which is the most interesting and most tricky is to demonstrate that these are existing. Okay, it's not very difficult to say that if this exists, if this integral is defined, this one is defined, and this one is defined, the sum is standing. The problem is under a relaxed situation. So if we don't take very strong conditions, or if we take much weaker conditions, to be precise, it might happen that some of those may not be defined. Okay, so that's the trick. There is also another thing which is important to understand is if ever we integrate the Radon transform on theta, so we do a partial integration, sorry, on R for each theta. So this looks like a function of theta. So we have the Radon transform of mu is a function of theta and R. So this partial integral looks like a function of theta. Indeed, it's always the same. And the reason why it's always the same is that it ends up summing over all the object, all the x and y. Okay, so we see, and you can have a kind of an understanding of that, is that when I sum here and when I sum here, at the end, I'm seeing all the object. Okay, and that's why the Radon transform, when I integrate it for one theta or for another theta, I get always the same result. Okay, so now what we say is that instead of measuring directly mu, I'm measuring the Radon transform of mu. Okay, and my point, the question I had at the very beginning was, am I able from this measurement to come back to this value? Okay. And I'm in real world. So basically, indeed, I'm not even measuring the radon transform of mu, but I'm measuring the discrete version of the radon transform of mu. So I'm discretized on a grid parameterized by r and theta. And indeed, what I'm trying to find out is not even the function mu, but it's a discretized version of this attenuation coefficient. So also on a grid, which means that basically I'm measuring a vector in r puissance, r power to r to the m being the number of couple r theta, and from that I'm trying to find out a vector in r to the n, where n is the number of couple x and y I'm measuring. I'm interested in. I want to know the measure of mu on. So and in this case, the radon transform is replaced by a discrete version of the radon transform, and it's fairly easy to demonstrate that the discrete version is also linear, which means that basically what I'm trying to reverse is the effect of a linear transform. So I have the radon transform in this case is a linear transform from r to the n to r to the m, which is basically a matrix, m by n matrix. So obviously I could, the first thing I can say is in the worst case scenario, I can always attack the problem using brute force pseudo inverse computation. So I'm just having a matrix mn matrix, and I would like to find a vector which, when it's multiplied by this matrix, provides something which is very close to what I measured. Okay, so indeed we could even maybe stop the talk now, because we know already it's feasible. We even have a recipe to do it, so why go on? Okay, so the problem with that is that this is a bit of a costly operation. Okay, the cost of this operation is basically computing the pseudo inverse of this type of matrix, and the computation of this type of matrix is a big O of the size of the matrix multiplied by the minimum between m and n. Okay, and to be honest, it's when we say that it's a big O, we are very optimistic, because indeed the constant of this big O is a very big constant. Okay, so if we have, for example, an image we want to reconstruct, which is a 1000 by 1000 image, so basically we want to compute mu on a grid which is making 1000 by 1000 point. It's just a 1 megapixel image. So if you consider what you have in your cell phone nowadays in terms of camera, you have a multi-megapixel camera. So this is completely outdated to be able to create a 1 megapixel image. But let's say we want to do a 1 megapixel image, and we'll say that to be approximately balanced between what we want to compute and what we measure, we are going to measure more or less the same amount of data. So we are going to have a detector which is 1000 pixel wide. So for each rotation, I'm going to measure 1000 values, and I'm going to do 1000 rotation, so that I end up having more or less the same number of data than what I try to estimate. Okay, then the computation is big O of 10 to the 18th. Okay, so that's a bit big, and as I told you, the constant by itself is already rather in the 1000 range rather than anything else. And then if we extrapolate, we realize that if I'm having an image which has a hedge of k pixel, indeed the cost of this inversion is big O of this to the power of 6. Okay, so indeed most of the problem of most of the concern in this problem is how I'm going from a problem which is solvable, which we can solve in a rather standard condition, to a problem which we can solve without spending too much energy on it. Okay, so to do that, we'll have a small digression through the Fourier transform. So the Fourier transform is something which is interested in periodic function. Sorry, I'm going a bit too fast. Before looking at the Fourier transform, we're going to look at the Fourier series. So the Fourier series is a decomposition of a periodic function. Okay. So if I have a periodic function, Fourier stated that we can decompose it as a sum of something which is constant and two periodic functions which are in quadrature phase. Okay, so basically we have a cosine and a sine. There are many other ways to see it, but basically we are going to say that this function is going to be the sum of functions of sine and cosine of the period, and then all the multiple of the period. Okay, so that's what we call in harmonic, for example, in music. And for example, a sound, which is a periodic signal, it can be decomposed in, so for example, a note of an instrument will be decomposed in a first harmonic, which is the note we hear in general, a second harmonic, which is the one which we hear at the octave, a third harmonic, which is the 12th, so that's basically an octave plus a quint, a fifth, and so on. And all these periodic signals are part of the complex periodic signal that we have, and this is because of these harmonics that we have some concordance between certain sounds. Certain sounds sounds better together than others, just because the harmonics fit on top of each other. So the signal that we hear is not too complex and too messy. Okay, so the nice thing about the Fourier series is that this decomposition exists, and it's even better because we know how to compute its constituent. Okay, so in this, when we say that this periodic signal f can be decomposed, we know that we can compute A0 as basically the mean of the signal over a period, and AN as this summation. Okay, so just to be clear, what we are doing now is to consider that we have a vectorial space of functions which are period of period p, and we are designing a scalar product. The scalar product is a summation over a period, so it's the summation, so it's 2 divided by the period, but okay, times the integral over the period of one function times the other function. Okay, so this is a scalar product between f and the function which is the cosinus, which has a period which is a frequency which is a multiple of the initial or the principal period. Okay, and what we are stating is that this is an orthogonal base, an orthonormal base. So these functions are orthonormals, so that when we do the scalar product, we get the projection, and by getting the projection, we can say that because it's an orthonormal base, the projections are also the coordinates of the function on this base. Okay, so this is basically a regular result using a scalar product and an orthonormal base on a vector space. So this is the simple way of seeing it. Now there is another way of seeing that, and I'll do it in an extra brief way. I don't know, I guess most of you already know perfectly well the complex numbers, but there are some extension to the real numbers, which are complex numbers. They are made of a real part and an imaginary part. Every complex number, so which I call Z here, is the sum of a real part, A, and a purely imaginary part, B times I, B being a real, and I being a number such that, a purely imaginary number such that its square is equal to -1. Okay, so this is one notation of a complex number, there is another notation which is called the exponential notation of a complex number, which states that we can write it as z equal the exponential of m plus theta I. And again, here you have a real number. This is a purely imaginary number because theta is real, so theta I is purely imaginary. And we have the relation where a, this one, is equal m times cos theta here, and b equal m times sin theta. And because of this, we call m, or more precisely, exponential of m the modulus, and theta the argument. Okay. So each of these notations have its own advantage. The first one, obviously, is nice because it's easy to do addition in complex. The second one, because since it's an exponential, it's easy to do multiplication, and a simple multiplication is somehow transferred to a simple couple of simple additions. And I realize that here is missing. What is module of z is exponential of m. I'm sorry, there is a mistake here, but okay. So we note, so it's the same r, sorry, then that's another problem, sorry. Yes. Okay, so for a complex number, we have a real part, which is noted this way, an imaginary part, and the module and an argument. And again, the module is not m, is exponential of m. Okay. Using this notation, we can also use complex numbers for doing this, the Fourier series. And the reason I show you that is that it's much simpler because f can be expressed as a single sum. So we don't have a specific case for A0. We don't have difference between A and B. We just have sum. And then basically, again, this means that we have still the same scalar product, which is this one, which is the integral over a period of 1 over p times the integral. And we have an orthonormal basis of the periodic function, which is exponential of 2 pi nx on p times I. Okay, so this is the base, and we project f on this base, and we say that once projected, the function is properly approximated if the sum is not finite, but if the sum is infinite, it's exactly equal to the sum of its projection on each of the basis vector. Okay, because of the way of the relation we have between m theta and the real and the imaginary part, we can derive that the two notation of the Fourier series are isomorphic, are completely equivalent with the relation which are. Okay. So these are periodics, but the objects we're studying are not periodic. So the reason why I started that, because it's simpler with a finite sum, but indeed our objects are not periodic. And one way of seeing a non-periodic object is to say a non-periodic object is a periodic object which periods tend to the infinity. Okay, so basically I'm saying I have an object, even a small object, and it's going to repeat itself, but I'm taking the repetition further and further away, so that the repetition of the object has less and less effect on the object itself. Okay, so by pushing my period away, by pushing up the period, I'm taking something which is repetitive and I'm making it look, and at the limit it will currently be a single object. Okay, so I have a repetitive object, I'm taking apart the repetition so that at the end I end up at the limit with a unique object. Okay, so that's what I'm doing by pushing the period to infinity. So at the end, when the period is infinite, whenever, which doesn't happen, but at the limit, if we think of it, we have just a unique object. It's not periodic anymore. And when the period tends to zero, tends to the infinite, 1 over the period tends to 0. Okay. And because my sum here is going to be on 1 over m, okay. If you look at this sum here, it goes on 1 over p. Okay, so these things are 1 over p. So it's n equal 1, so 1 over p. Then the second one is 2 over p, and so on. Because of that, this summation is going to get values which in terms of this part are going closer and closer as we go on. Okay, so we transform this discrete summation into a continuous summation. The problem that we have is obviously 1/p is going to be 0, and the reason why I have things going on is that because n is also growing. As I'm going with 1/p going to 0, I'm going to consider some n's which are higher and higher. So if I write, I cannot write anymore n times 1/p, because this is not very clear what I'm going to do, because both of these are going to be big. So the best is to write directly n/p, and this I will call it eta. Okay. So now at the beginning I was telling you about sounds. Sounds are a signal over time. So in sounds, the x is time, and in this case, what eta is what we usually call or colloquially call a frequency. Okay, so we can talk about also, we tend to talk about a space domain or a time domain and a frequency domain. One variable x is in the space domain or in time domain, and the eta is in a dual space, which is a frequency domain. Okay, and in this case, we're going to represent the function f by another function. It's not a series anymore, because we have an infinite number of coefficients, and the density of coefficient tends to infinite as well. So not only the series had an infinite number of coefficients, but they were discrete. Now we have a continuous number of coefficients, so we write it as a function on R, and for a given frequency, I will have a value which is this integral. Okay, and here you remark that we have more or less the same scalar product. Instead, the period now is going from minus to plus infinite, because it's an infinite period, and and I have a function which depends not anymore on something which is discrete, but on something which is continuous, which is this eta. And we have the same inverse formula as before, and it's not a regular sum, because I don't have any more discrete coefficients. I have continuous coefficients. So now the sum itself, so the sum, which was a scalar product, was an integral on the period. Now it's an integral over all R, and the summation, which was recreating the function from its coefficient, is no more a discrete series, but it's a continuous integral, also on the same domain. Okay, so by the way, we see that it's very symmetrical. It's just a sign of the oscillation part in the exponential which change. And as the Radon transform, the function, the Fourier transform, the operator which takes f and produce f hat, is a linear transform. It's fairly easy, and that relates also to the fact that that it's mostly an integral transformation. In the Radon transform, I had this. I decided from the beginning to consider the Radon transform only a function which had a compact support, which were continuous, had finite value. And the nice thing about the Radon transform is that if I take this condition, what I obtain is also a function which has finite support, which is continuous, and which has finite value. It is not the same with the Fourier transform. Fourier transform is much more tricky, and one of the problems of the Fourier transform is, basically because I'm growing the period, I'm going to have energies which is, so part of this integral. Sorry, if one of the functions has compact support, the other one has infinite support by construction. So it's more tricky even than before to make sure that all the integral are existing. So the condition to make sure that both the transform and its inverse are working are a bit more complex to express. This is a function, f is a function which takes a real number and provides a real number. Indeed, we could also have taken a real number and provided a complex number, in which case we'd have had a bit different things in the complex notation. But what I'm really interested in is objects which are 2D. Okay, so what I'm going to do is to do extension. And indeed, the reason I can do extension is because basically what we see here is that the argument of the exponential, the only place where I have x and eta having a real importance is in the exponential, and this is a product of eta and x. Okay, so I can replace this product by a scalar product. Okay, so either I consider x and eta to be in the same space, and this is really a simple scalar product, or they are in dual space, and then I'm applying, because they are in dual space, I'm applying eta form to x. Okay, but okay, to make it simple, I will say I'm applying the scalar product of a vector in the time domain with a vector in the frequency domain. Okay, and I can write it more or less the same. So you see the only difference. So this is a vector now. That the problem with my Greek font, it doesn't have bold, but this is a vector. This is a vector eta in 2 dimensions, and I have a scalar product which appears in the exponential, and the same here. Okay. F is still a real valued function. That is important to work, obviously. This has to be a real value. So this is times a real value, again, because all the vector part, all the vectorial part of the computation is done in the scalar product or its external product. Obviously, I could do that in any type of number of dimension I want, but in this case, I'm only interested in 1D and 2D. So basically, we saw that the Fourier transform can be applied to 1D or 2D object, or 2D function, or even a higher dimension function. There are some places where I will be dealing at the same time with Fourier transform in 1D and 2D. And in this case, just to be absolutely clear, I will put the number of dimension in the index of the Fourier transform. Okay. Okay. Now that we had this discussion across the Fourier transform, there is a result I will not go too much into detail about, but and the reason why is that it's a nice and not so complicated exercise for you to take the formula of the Fourier transform here, and to take the formula of the Radon transform that you had before, and to realize that just by inverting the sum. So again, the most tricky part in this case is not to get this result, but is to make sure that what are the conditions in which this result can stand, because basically the main problem with these integrals are not to compute them, but to make sure that you can compute them. Okay, so this is the trick in this case. But so we have a real space. It's Fourier dual space, which is basically a frequency domain space in this case. And there is a theorem which is called Fourier slice theorem, and it states that the projection is basically a Radon transform. I take all, so by projection in this case, what I mean is that I'm taking all the integral of a straight line and I'm projecting it at the end of the line. So this is a Radon transform in real space. Can be replaced by a section of the Fourier transform in the dual space. Okay, so if you put it in other words, if I'm taking the 1D Fourier, and that's how you do the computation. And again, the computation is the easy part. The difficult part is to make sure that what are the conditions for all the integrals that we write are holding properly and are behaving nicely. But if I'm taking the 1D Fourier transform of a Radon transform of theta at a given theta, so basically I have my mu function, I'm applying the Radon transform, and the Radon transform for a given theta is a single, it's basically a function of a single real. Okay, so it's a 1D function. The only parameter, the only variable I have in this function is the R parameter. Okay, so if I'm taking the Fourier transform of this, okay, I'm expressing it. I'm just inverting a few sums because they commute. This will be exactly the Fourier transform of mu over a section of the space which is orthogonal to theta. By orthogonal to theta, what I mean, it's a bit tricky because theta is in this real space where this is living in the dual space. By orthogonal to theta, I mean it's a section which is all the coordinates u for which u times for which U is a direction of theta in the real space, yes, and that's basically all the value of the Fourier transform on frequency eta, such that this frequency is orthogonal, that is, its scalar product with this unitary vector is new. It doesn't have to be unitary, by the way. It can be anything which is not zero, but okay. So this theorem is really interesting because it somehow relates what I'm doing. I'm performing Radon transform, and what it tells me is that I have a result about the Radon transform and the Fourier transform. And the nice thing about that is something I didn't explain much more earlier, but the Fourier transform, what we saw is that we have an explicit inversion. Okay, so the inversion of the Fourier transform, so going from a Fourier transform to the real function is done by just summation. Okay, so now let's look at all this together. I'm doing the experiment. I'm doing the experiment by doing the measurement of the Radon transform at different angles. So basically, I'm going to measure the Radon transform at different angles. So I'm measuring the intensity coming out of on the detector. So the first thing, obviously, I have to do is to compute the absorbance. Okay, so for each pixel of the detector, for each angle, I have to compute the log of I0 over I1 transmitted part, and this is basically I'm estimating the Radon transform of mu at a given theta for each angle I'm computing. Okay, on this one I will compute the Fourier transform, and what the slice theorem tells me is that somehow what I'm computing is for example, if theta is this line, I'm computing on an orthogonal line. So on this one, I'm computing all the value of the Fourier transform on this line. Okay. And I end up, so if I do all the theta, I end up with a sampling of the Fourier transform of mu over on this polar grid. Okay, so I'm estimating the Fourier transform, the 2D Fourier transform, because we are now in 2D, so it's U and V in this case, over all the possible angles up to a certain level, and the level is basically depends on the discretization I'm taking. Okay? So I'm computing all these, and with each of the radiograph at each angle, I'm going to populate one of these lines in the Fourier domain to the computation of the 1D Fourier transform of the Radon transform. Okay. Okay. So what I can do now, because I know how to do the reverse Fourier transform, is to compute the inverse Fourier transform of the function that I have sampled here. The main problem I have is that the summation scheme which is simple is to have integration over a Cartesian grid, a rectangular square grid or a rectangular grid, which is absolutely not the case I have. Okay, and one thing which is obvious is that well, I will come back to that a bit later. But so if I want to be able to compute in a fairly easy way what we call the back Fourier transform, so the inverse of the Fourier transform, one thing I can do and is doing the resampling of the Fourier domain in a Cartesian grid and do the computation of the 2D inverse, and that would solve my problem. Okay. The thing which is really tricky in this case is this resampling indeed, because the relationship between the Fourier domain, the frequency domain, and the space domain or the time domain are quite complex. And what is very local, so when I'm doing an approximation, so for example, if I'm approximating a point here, often I would tend to approximate a point here by using just the neighbors. So I'm doing something very local for the interpolation. What is local in one domain is diffused over all the dual domain. Okay, so if I'm doing something which is local in frequency, basically it's saying that at this point, the value of the Fourier transform at this point is the average of these four. Okay, just because I'm in the middle of these four. This is a very local measure. Indeed, what I'm doing in terms of approximation is an approximation which is spread all over the space in the reverse space. So I have to be careful to find a scheme which is both local on both sides. So I could also have the opposite, saying what is really important for me is to perform an estimation here, which ends up having a pure local effect in the space domain. But then to be able to estimate this point, I will have to use all the value in the Fourier domain, which is computationally not effective. Okay, so I have to be very careful to have something which is kind of local in both space, and that's not trivial. Okay, so that's one way of doing it. There is another way of doing it, and which is the one which is the most often used, which is called the filtered back projection. Okay, so we're going to do it without doing the resampling, and we replace the resampling by something else. Okay, so we consider that the Fourier space is, the Fourier transform is linear. So basically, if I have a function in the Fourier space, I can do the reverse of the Fourier transform piecewise. So I can somehow here, oops, sorry. Here you can consider this is somehow a pi, and instead of computing the Fourier transform, which the back Fourier transform of all this, I will compute the back Fourier transform of a pi. So for computational reason, I better have symmetrical kind of piece of pi, but I'm going to compute something which is a sector here, which is symmetrical to the origin. Okay, and I say the back transform of all this is a sum of the back transform of all these little sectors. Okay, so I cut the Fourier space in angular sectors, and I'm going to do the inverse Fourier transform on each of the sectors. This is I have the same problem here, basically. So the problem is that I have a shape which is a bit tricky here. Okay. Now there is something I know how to do, is if instead of having an angular sector, I have a straight line. And indeed the thing is this is a slice theorem again. So if I have a straight line, the back Fourier transform of this by the slice theorem, you realize that this is a function which on this direction is the back Fourier the 1D back Fourier transform of what is on the line, and on the other direction is constant. Okay, so it's a bit like you have a shape which moves along orthogonally to your projection, and on the other side is constant. Okay, so that's why we call it back projection. So I'm going to have a shape, and I will project it perpendicularly. Okay, so I can do that, and I can say, okay, I'm going to approximate each of these sectors by this. I say, okay, they are more or less the same. So instead of doing the back projection of this one, I'm doing the back projection of this one, and I'm doing the sum. If I do that, I will have a small problem, because basically the center part will be copied over, while the extreme parts are going to take less weight. Okay, so I have a problem of weight here if I'm doing that. And typically the origin is going to measure n times. It will have n times its effect compared to the very end, because it's exactly the same in all the projections. Okay, so the idea is, instead of doing that, I first apply a weighting on this line. I apply a weighting such that I'm saying I have something which looks like that in terms of weight, but in terms of shape, this is the shape I have, so I can do the reverse. Okay, so basically now what I'm doing is I'm saying I had computed the 1D Fourier transform of the radon of the projection. This leads to something which looks a bit like that. In the Fourier domain, I'm applying this type of weights, and then I'm doing the back projection, so basically doing the reverse Fourier transform of this, and splatting it over perpendicular to the direction, so basically splatting it over in this direction. Okay, and when I think about that in terms of signal processing, obviously what I'm doing when I'm taking this Fourier transform here and I'm multiplying it by this type of function, this type of weighting function before computing the back Fourier transform. What this is typically a low frequency filtering. So basically, I'm reducing the low frequency and I'm amplifying the high frequency. Okay. So instead of doing the Fourier transform, taking the radon, doing a 1D Fourier transform, applying a weighting and doing the back filtering function, I can just replace all this by just a filter. And then I do the back projection on the filtered version of the radon. Okay. And that's the nice thing is that this is a numerically well understood transform because the filtering is well understood and so on. Okay. So now I'll show you just the image as it goes. Okay. So here, what I show you is a radiograph. I took a 3D object so that we have a bit of thickness, but indeed what we're interested in is just the middle section of it. Okay. As we take the radiograph, for each radiograph, I'm computing the filtered version of the radiograph, which is not displayed here, and then I back project it on top of the rest. Okay. So as I'm doing the rotation, on the same time I'm doing the rotation, as the rotation is going on, I can do the summation, okay? And at the end of the summation, I get something which is fairly resembling to the object I'm trying to reconstruct. Okay? So now, obviously, there are something which are important, and one of them, in terms of quality of the image, is the number of angle, and that's something I mentioned to you at the very early stage when I was mentioning the cost of the full inversion. I was telling you that since we are in a linear system that we try to inverse, we have to make sure that the number of observation is in the same range. The number of observation is in the range at least equal to the number of estimation that we want to get. On tomography, there is this weird effect of mostly of the Radon transform, is that somehow every pixel on the image, okay, so every pixel of, or more precisely, a pixel of this image is going to be present or will affect a lot of the image of the pixel of this image. And because of that, we have a system which is rather dense, and we can manage to have things which are a bit more scarce. Okay, so there are some high level of regularity. The system, if we look at the matrix of the Radon transform is a rather dense matrix. Okay, still, if we go for this type of things, so basically now I'm doing the image I was presenting to you now had more or less 1,000 pixels in width. So this is a 1 by 1,000 1,000 by 1,000 square image. And here I reconstructed with 1,000 projection. The number of pixels of the projection is exactly the number of pixels of the image, but I can try to have less projection. And if I have less projection, what I'll see is this type of effect. Okay, so I have an effect, basically artifact. If I lower the number of projection, because some pixels, the pixels which are close to the center, ends up in many more projection than the others, they have a better approximation when I'm doing the reconstruction compared to pixels which are on the edge of the object, which basically end up in fewer projections. Okay, and that's why if I'm doing too low a number of projection, I will have introduced quite strong artifacts, but those artifacts are localized on the periphery of an object. Okay, and with that, I think I'm done for the main subject of the talk. I think I have a few minutes more, so I will go on a few other aspects concerning the reconstruction. What I was speaking of at the very beginning was the interaction we are trying to measure. So we are measuring what I was telling you from the beginning is that the main effect of X-ray with matter is what we call absorption or attenuation. Okay, so mostly what's going on with an X-ray when it traverses matter is that it's absorbed or it goes through without being altered in any way. And that's what we call absorption or attenuation. Okay, so basically, I don't have my mouse on this system. Okay, so on the top, I represented something which is attenuation. On the bottom, I have another object which is less attenuating. On an object which is less attenuating, because there is not so much attenuation, I can see small effects. So it's easier on this type of object to see small variation of the effects. And indeed, what's going on is that the X-ray is not exactly going, the interaction between the X-ray and the matter is not exactly only attenuation. It also has some kind of refraction effect. Okay, so refraction effect is the effect which makes light being divergent if it goes through water. So for example, if you look at me through the glass of water, you will see that the shape is completely deformed, and the reason why it's deformed is because the ray, as it's traversing between air and water, it's being refracted, so its direction is going to change a bit. Okay, and because of that, at the place where the effect of this is stronger at the place where the ray are more or less or are close to parallel to the interface. Okay, so this is an effect which is important when the ray is close to tangential to the interface. Okay, so in the bottom image, the place where this effect of refraction, so the change of direction of the X-ray is important, is at the limit between the different part of my object. These parts, because they are in this image, these parts are parallel to the beam, so they have an effect on the intensity of the beam. But because the rays are a bit displaced, they are disoriented, the orientation change a bit. It means that we are going to we're going to have a small variation. If we just next to the object, we're going to have small variation in the attenuation. But if we go a bit further away, this refraction start to have effects, and it displays the energy of the light. And it's typically what you see, for example, if you have a glass of water in a sunny place, where you see that you have some kind of a lens effect, and this lens effect is visible if you put your observations far enough so that the angular effects start to be sufficiently important compared to the attenuation effect. Okay. The fact is, funnily enough, is that if you do the reconstruction without trying to correct for that, it has the effect of creating artifacts at these borders. And you see, for example, in this case, so this is a fossil sample of a tooth, which is a few million years, by the way. And you see at the very top what you obtain when you do the measurement very close to the detector. So basically, you see only the attenuation effect. And as you go away from this, you start having stronger contrast on the edge, so on the edge of the materials. Okay, so it's easier to see the limits, the interface between different material on this aspect. Okay, the other result is you see it better, you have higher contrast, but the position is less precise somehow. Okay, and you can see that if you do so this is the equivalent reconstruction, so simulating the same object, but either with pure attenuation on your left and using having something which is mostly or it's dominated by the effect of refraction on the right, and you see typically that definitely the reason why you see something on the right is because you have this edge. The contrast is reinforced by the edge, but as you go further away, the position of the ripples which are generated by the reflection is going to go away from the position of the interface. You have basically two ripples, one on each side, and because of this, the position of the interface itself, at the same time you see better the interface, but the position of the interface is not as well defined as in the initial case. Okay, so again, this is a simple propagation, and again, the funny thing is that in this case, again, the best way to do the computation is to go to the Fourier domain for completely different reasons. So it's another place where we use a Fourier transform in having a mathematical model of physics for being able to do proper application on and properly using physically measured entities in terms of understanding objects. And with that, I think I'm done. Thanks a lot.
So if anyone has any questions, you can ask them, and I'll read them to Serge Cohen. There was one question in the lecture, but I think that you've already answered it. The question from Youssef Ben Fattah: how can we construct F using the figures? But it was the objective of the last part. So I think it's already answered.
I can go. So sorry, I can take this as an advantage to go for a small comment.
Yes.
There is some kind of a scam in what I told you. The reason why the reason we didn't stop. Sorry, at this point, I say we know how to find the solution. It's costly. Okay, so at this point in the talk, I told you because we are just in a linear problem of finite dimension, we know how to solve it, and we might say that there is no need to go further on. Okay, and I say the reason why we want to go further on is because of the cost of the computation. So if we do it brute force, it costs too much, and that's why we want to try to be a bit more smarter. The place where there is a bit of a scam is I didn't tell you how much does it cost to do the rest. And indeed, the funny thing is the level of detail that it entails. Okay, so in this case, if I'm doing this version of the computation, I have so the first thing which is super important in all of this is Fourier transform is a linear transform. So normally to transform an n space to an n space, because we have more or less often the same number of parameters in one space to another. So to make it simple, we have an n space to an n space. So normally it's n square. Okay, so it's a linear transform, so it's a multiplication by a matrix. So if you go from n to n, it's n square, the cost of a Fourier transform. And once I know, and if I have the operator for the back Fourier transform, it's also n by n operation. It ends up that there was some algorithm which were developed for the Fourier transform, which are called the fast Fourier transform, where by a divide and conquer strategy, the cost of the Fourier transform, instead of being n square, is n log n. Okay, so the fact that we're going through the Fourier transform makes the transform less expensive. That's the first thing. Now we have to consider that we have a Fourier transform for each projection, and we have n projection again. So it ends up being the Fourier transform in one direction and then the Fourier transform in the other direction. They are the same cost. They are n square log n. The resampling is very costly, but the resampling is n square, because the resampling is basically the number of dots here. So it's n square times, and the constant is more or less the size of the kernel. So how many neighbors I'm going to use to be able to compute. And that's the point which is tricky, to get a low cost on the interpolation. I need to use as few as neighbor as possible, but the less neighbor I'm using, the more long range effect I'm creating because of this interpolation. And that's the problem of this method, is that I have to find the proper balance between the cost and the somehow ripple effect, long distance ripple effect I have in the reconstruction. But the cost of this method is basically n square log n, where n is for a single slice, where n is the width of the slice. This method is again, indeed, it's also it may look as if it's n square log n, because basically for each of those I have n members. I have sorry, I do the if I don't do the last step, so basically if I don't consider that, if I'm really going to the Fourier domain, for each of the projection I have n log n, because I have a Fourier transform forward and reverse. It's the same cost in terms of big O, and I have n of those, so it's n square log n. If I'm able to do this filter using a linear, a simple kernel approximation, instead of having n log n, I have something which is n times the size of the kernel. But the size of the kernel may be fixed, so basically it ends up in the big O. It starts to be a big constant in the big O, but it's a constant in the big O. So basically, by doing the retro projection, I may have the feelings that I'm going from n square log n to n square, which is nice. The only thing I'm hiding here is that I have the back projection. The back projection is super expensive, because for each of these value, I'm going to have to distribute it over all the image. So for each of those, I'm going to attribute an addition, a simple addition. It's not very costly, an addition, but I have it to be over all the image. So, so indeed, I have something which is n to the cube in terms of big O. So then the problem is definitely between the two methods is a constant, because if it's a small constant, n cube may be smaller than n square log n with a big constant. But so it's really a matter of n, and or more precisely of the respective size of n and the constant. And indeed, what we see is that the bigger the dimension of the image, the more interesting it is to do what we call regridding, because this is really big O of n square log n. So the constant might be enormous, but if n is big enough, it wins. Okay, so until now, people will never do that because it was too costly, and it's really a matter of concern. That's the funny thing. It's something which is recent. Until recently, nobody would do that because it was too costly. And nowadays, people say, okay, well, I'm not doing that. This is too costly. But again, that's the thing. When we are in a theoretical world, n square log n is always better than n cube. But in real world, it really depends on the constant. That's it. That's a way to go over the reverse of the Fourier transform.
Thanks very much. There seem to be no other questions right now. So Serge, Cohen, I'd like to thank you again for this very nice lecture, and also for being part of organizing the visit of Soleil yesterday.
Well,
these two, the visit and your talk go very well together. Thank you very much. We were very happy to have you.
Thanks. And
I'd like to. Oh, sorry. Say again?
See you in 2 years, maybe.
See you in 2 years. Yes, definitely.